What is up, Mathverse? Welcome back! This is Cedie and welcome to Cedie's Mathverse. So for today's video, I will be discussing the change of base property, which is a property in logarithms. Without further ado, let us get right into the topic. The concept of logarithms has helped people throughout the years since its invention in the 1600s. From determining the population growth, measuring the magnitude of various earthquakes, and determining the growth rate of various pathogens such as COVID-19. But what is the definition of a logarithm? Logarithms are defined as the inverse function of exponential functions. Let us consider this exponential equation: 3 squared equals 9. As you can see, the number 3 in this equation represents the equation's base. Meanwhile, the number 2 in a superscript is the exponent of the exponential equation. Furthermore, the right-hand side, which contains the number 9, gives us the answer to the exponential equation. However, in logarithms, they are expressed differently. Consider this logarithmic equation. The logarithm of 9 base 3 equals 2. Here, it has 4 parts. The first part being the logarithmic notation itself, which is the letters log, log. The next one is the logarithm's base, which is in a subscript. Here, it is the number 3. The third part of a logarithmic equation is the final answer in the exponential equation earlier. Here, it is the number 9. And on the right-hand side lies the last part of the equation, which is the exponent in the exponential equation earlier, which is 2. Basically, every logarithm is of form the logarithm of m base a, where the log represents the logarithmic notation or symbol, the letter m representing the base of the logarithm, and the letter a being any positive real number. There are 2 special types of logarithms. The first one is when the value of the base m equals 10. This is called as the standard logarithm, and the number 10 is removed, which means that the remaining constituents on the logarithmic expression are the logarithmic notation log and a. This means that if you saw a problem with a logarithm with no base, it is automatically base 10. The second special form of logarithm occurs when the base m is equivalent to e, which stands for the Euler's constant. It's pronounced as Euler. This is known as the natural logarithm and has symbol ln. Did you know that the logarithms have a property? The logarithm of a base m is equivalent to the natural logarithm of a over the natural logarithm of m. To prove that this is indeed true, try evaluating the logarithm of 8 base 7 and the natural logarithm of 8 over the natural logarithm of 7. As you can see, the result is both 1.06862. If you still don't believe this is true, you can try it for any other logarithmic expressions, and this will always hold true. Now that I have discussed some stuff about logarithms, let us now introduce the change of base property. The change of base property states that the logarithm of a base m equals 1 over the logarithm of m base a for all positive real numbers a and m. But how did we arrive with this idea? Consider this proof. I mentioned earlier that the equivalent value of logarithm of a base m is the natural logarithm of a over the natural logarithm of m. Following the similar logic, we have the logarithm of m base a is equivalent to the natural logarithm of m over the natural logarithm of a. Now, from the change of base statement, we substitute what we have obtained in the last two steps. Thus, we have the natural logarithm of a over the natural logarithm of m equals 1 over the natural logarithm of m over the natural logarithm of a. Then, we get the reciprocal of the right-hand side, which gives us the natural logarithm of a over natural logarithm of m equals natural logarithm of a over natural logarithm of m. Thus, the statement is indeed true. All you have to do is to just interchange the position between the base and the other number. And that's it. Change of base property. Now, here's an example problem. Evaluate 1 over logarithm of 11 base 3. As we can see, this is just a direct application of the change of base property. All we have to do is just to interchange the position of 11 and 3, then get the multiplicative inverse of the resulting logarithm. Thus, we have logarithm of 3 base 11. Easy, isn't it? Now, let us add some spice in the next problem. How about evaluating 1 over logarithm of 11 base 3 plus 1 over logarithm of 11 base 37? At first glance, it looks like it is impossible to solve this problem without consulting a calculator. However, if you know the change of base property, it becomes a lot easier. So, we just need to switch the base and the output for each term in the problem. This leads us to getting the value logarithm of 3 base 11 plus logarithm of 37 base 11. Now, we know that one of the properties of logarithm is its addition property. It states that logarithm of a plus logarithm of b is equivalent to logarithm of ab. This gives us logarithm of 3 times 37, which is equal to 111 base 11. And that solves our example problem. Here's a little exercise for all of you. Given the expression 1 over logarithm of 13 base m plus 1 over the logarithm of 13 base a. If am is equivalent to 2197, what is the value of the above expression? Try to share your answers and approaches in the comment section below. So that is all for today's video, Mathverse. I hope you enjoyed this video, and if you did, please leave a thumbs up as well as subscribe to Cedie's Mathverse. If you want to suggest some topics or improvements, kindly leave them in the comment section below. See you guys next time, and always remember, mathematics is incomplete without you.